Hey, it's Mr. Shrum, and welcome back to another lesson activity walkthrough. And today we're looking at the structure of the atom lesson activity called Rutherford scattering. And in this activity, we're going to use a simulation to explore the different atomic models scientists have created over time. To begin, we're going to click the plum pudding atom tab to view Thomson's model of the atom. The red cloud represents the positive charge, and the white dots are the suspended negatively charged electrons. We will use the gun to fire alpha particles onto the atom. Recall that alpha particles are positively charged particles that are smaller than the atom. So for part A, let's look at what we should be considering. If the plum pudding model of the atom is correct, what should happen to the alpha particles when they pass through the cloud? Well, let's check out the simulation. We're gonna go with plum pudding right now. So as you can see, the red cloud is the positive charge in the legend here. And these tiny ones are electrons. These tiny white, bluish, grayish on my end. But here we go. We're going to use the gun. This is the tin foil. And we're zooming in on that very small section here. So on the atomic scale, this is 3 times 10 to the negative 10 meters. Very small. And you see that we're shooting these alpha particles, these positively charged particles, through the electron cloud, the plum pudding model. And if this were the case, they would all pass through. And you can kind of see the trails if you click the trace button. You can also increase the energy of the alpha particles. But no matter at what speed, it looks like these alpha particles are not stopped at all. And their course is not altered in the slightest. So we'll go back. If the plum pudding model of the atom is correct, what should happen to these alpha particles when they pass through the cloud? Well, it looks like they're just going to pass through without any change in direction. Now, part B, in the simulation, select the traces checkbox we did, and then select the correct option from each drop-down menu. The alpha particles are not deflected by the atom. This behavior let's see. So traces. Yeah. So if you look at the traces, it's all straight, no deviation. So that would support the plum pudding model. No deflection. Part C. Now switch to the Rutherford atom tab at the bottom of the screen. In the upper left, click the red and gray cluster. This model represents the positively charged nucleus. So now we're introducing the nucleus. If this model of the atom is correct, what should happen to the alpha particles as they pass through the atom? So we're going to go to the Rutherford atom. You see each one of these is a nucleus surrounded by the electron energy level. So this is all one, this is another, this is another, this is another. But we click on this gray and red cluster. So this is just one nucleus that we're paying attention to. We're going to shine alpha particles at it. Oh, it looks like the particles are deflected away from this nucleus. That must mean it's a positively charged nucleus. The alpha particles that come close to the nucleus should be deflected away from the nucleus. In the simulation, select the traces checkbox and then click the blue dot on the gun. Select the correct option from each drop-down menu below. All right, so traces. Now you can see, let's speed it up a little. You can see how their paths diverge by following those trace lines. Alpha particles are deflected. This behavior supports Rutherford's model. There's a good picture of it. The model did not predict that the alpha particles would be deflected well before reaching the nucleus. So there's that as well. When Rutherford ran his gold foil experiment, he expected to see results like those in the plum pudding atom. Instead, his experimental results were closer to those seen in the Rutherford atom simulation. Why can't the plum pudding model of the atom explain Rutherford's experimental results? Since some alpha particles were deflected, the atom must contain a small region with a strong electric charge. Since most of the alpha particles were not deflected, the atom's positive charges must be spread thinly across the large region. Since some were deflected, the atom's negative charges must not be attracted to the alpha. Since most of the alpha particles were not deflected, the atom's negative charges must exist in a thin cloud around the atom. The only one that makes sense here, since some alpha particles were deflected, the atom must contain a small region with a strong electric charge. Rutherford found that his experiments did not completely match his assumptions or the plum pudding model. Although most particles passed without much deflection, some were deflected at small angles, and a few were deflected back to the source entirely. So there had to be a positively charged region that deflected some of the particles. Only a few particles were deflected at large angles, indicating that this region must be very small. Because the results went against his assumptions, Rutherford went on to propose a new atomic model. And in this model, the atom has a positively charged nucleus at the center with the electrons orbiting it in a set path. And then we have another lesson activity dealing with ions and isotopes. And this activity, we're going to look at how an atom is made up of neutrons, protons, electrons. We're going to use a simulation to learn how adding or removing these atomic particles affects the identity of an element, its net charge, and its mass number. When expressing net charge in chemistry, the positive or negative sign always comes after the digit. For example, 2 plus is a net positive charge 2. However, you'll notice in this simulation that the standard convention is reversed, so positive 2. We're going to open the simulation, select Atom tab, and expand the net charge and mass number boxes. Atom. Expand, expand. Okay. So question 1, part A. Drag a proton to the center, marks X, representing the nucleus. Select the correct option from each drop-down menu to describe what you see. Let's check it out. We'll cut that. 1 proton. Ta-da! Okay, it looks like we have a net charge of +1 and a mass number of 1. Hydrogen. Nice. Now we're going to drag a neutron to the center, representing the nucleus. What do you observe? So we got 1 proton already, and it's hydrogen. Now we have a neutron. And the net charge is still +1, but the mass number is now 2. Mass number increases to 2, net charge remains +1. And then part C. Next, drag an electron to the outer orbit. What do you observe? So we're going to have one of each now. We have a neutral atom. Net charge is 0. Mass number did not change. We can see how it's stable or unstable too. So let's remove that electron. Still pretty stable. Nothing changed in the stability. All right. Part D, drag a second electron to the inner orbit. What do you observe now? Okay, one more electron. Now we have a net charge of -1. Mass number is still the same. It remains hydrogen. Mass number doesn't change. Net charge, -1. Continue to experiment with adding protons, neutrons, and electrons to the atom. You can also drag the particles from the atom back to their baskets. Note how these particles affect the identity of the element, net charge, and the mass number. What determines what element the atom is? Well, it's the number of protons. And to check that, just keep adding protons. Helium, lithium, beryllium, boron, carbon, and so on. You can keep adding neutrons to make it more stable. There we go. Okay. And then part F, while adding and removing particles in part E, you probably noticed a change in the overall charge of the atom. Which statements about the net charge of the atom are true? Select all the correct answers. The atom has a negative charge when it has more electrons. True. When the protons outnumber the neutrons? No. When the protons outnumber the electrons, it has a positive charge. Well, if there's more electrons than protons, it's negative. If it has more electrons, I'm sorry. If it has more protons than electrons, it's a positive charge. More electrons than protons, negative. Exactly what it says here. Part G, a change in the number of particles changes not only the charge on the atom, but also its mass number. Based on your observations of mass number, complete the statement to explain how mass number is calculated. Revisit the simulation as needed. An atom's mass number is equal to its number of protons added to its number of neutrons. Neutrons plus protons equals the atom's mass number. And that's it for the lesson activities in the structure of the atom. If you have any more questions, please let me know. Message me in Canvas, and I will help you out as soon as possible. But until next time, have a good one, and I will see you all later. Bye-bye.